the mean value theorem is an extremely important theorem in analysis. In this video, we're going to study its statement, see what it means geometrically, learn about some extremely important consequences that this theorem has, and we're not going to prove this theorem in this video, but we're going to see which results we need to prove in order to be able to prove the theorem later on. So let's get started. The mean value theorem tells me that if I have a function that satisfies these two conditions, that I know that f is continuous on a closed interval ab and f is differentiable on the open interval ab, then there exists a point c in the interval ab such that f prime of c is equal to f of b minus f of a over b minus a. Something interesting about this theorem is that it is an existential theorem. It tells me that such point C exists, but it doesn't tell me how to find it. So in a way, it's similar to what we had with the intermediate value theorem, where, again, we were able to find a point C that satisfies certain properties, but we couldn't say C should be this thing. We just know it exists. So with this in mind, let's try to see if we can take a closer look at the conclusion of this theorem and see if we can interpret it geometrically. So you see, the conclusion of the mean value theorem tells me that there exists a C such that f prime of C is equal to f of b minus f of a over b minus c. If we look at the right hand side of this equality here, that is just the slope of the secant line passing through the point a f a and b f of b. And f prime of c, well, remember that the derivative is just the slope of the tangent line at that point. So f prime of c is just the slope of the tangent line to the graph at the point c f of c. So what this theorem is telling me is that at least one point c, we have that the tangent line to the graph at that point is parallel to the secant line passing through the points a f a and b f b. Okay. So why do we care about the mean value theorem? Well, it has some extremely important applications. It will allow us to prove that if I know that a function has zero derivative everywhere, then the function has to be constant. It would allow us to know that if the derivative is positive, then the function is increasing. We'll use it to prove the fundamental theorem of calculus, L'Hopital's rule, all integration methods depend on it. Many more theorems in analysis really need the mean value theorem to be proved. So that's why we think of the mean value theorem as probably the most important theorem in analysis. Okay, so now as I said in this video, we're not going to give a proof, but we'll give a structure of the proof. We want to prove the mean value theorem. But to do that, we're going to prove another theorem called Rolle's theorem. And actually, it is equivalent to the mean value theorem, but it looks a bit simpler. It's a bit easier to work with, so we're going to handle that one first. And to prove this Rolle's theorem, we're going to use two theorems that we already know. We're going to need the extreme value theorem and the local extreme value theorem to prove it. So these two theorems in pink, we've seen them in previous videos. So the idea is going to be combining the use of these two theorems to obtain Rolle's theorem, and then we're going to use Rolle's theorem to obtain the mean value theorem.